Every second, billions of background conversations are happening right around us. Smart cities monitor power grids, cloud servers route global financial data, and autonomous devices communicate their exact coordinates in real time. But this dense web of interconnected communication is fragile. A single failure in a routing protocol can cascade through the network, causing significant real-world disruptions. You cannot safely test an experimental communication protocol by pushing it live to a working city grid. The risk of crashing existing services is too high, and building an entirely separate physical replica of that infrastructure just to test on is often cost-prohibitive. This is the exact engineering dilemma that OMNeT++ solves. It is an open-source simulation framework that acts as a virtual proving ground. It gives network engineers a safe sandbox where they can build, break, and optimize complex communication systems long before any hardware is deployed. But there is a mathematical catch. Simulating the data flow of an entire city would overwhelm a standard computer if it tried to process every single microsecond of time. To make these simulations possible, engineers must move away from the concept of continuous time. To maintain efficiency, OMNeT++ operates on a principle that entirely skips the empty and active space between actions in a network. This chart illustrates the core difference. The top timeline shows a continuous model, tracking data like a smoothly flowing wave. The bottom timeline shows a discrete event simulation. The engine strictly jumps from one specific action to the next, analyzing only those isolated dots and ignoring the gaps between them. Here is how that looks in practice. The timeline registers the exact millisecond a data packet is sent. Then it instantly teleports to the exact millisecond that packet is received at its destination. The dead time while the data travels through the wire is bypassed. Slicing time into these discrete events provides a distinct computational advantage. It allows a computer to process thousands of simultaneous data transfers, simulating years of complex network activity in minutes. This timing engine is the invisible heartbeat of OMNeT++. But for the simulation to be useful, it needs actual network components to process. Calculating the timing is the foundation. The next step is using that engine to virtually assemble the network's physical architecture from the ground up. Users rarely need to write the code for an entire system from scratch. OMNeT++ utilizes a modular architecture based in C++, relying on reusable components. This is the INET Framework. It acts as an essential library of pre-built, standard internet protocols for OMNeT++. These are the building blocks of the simulation, pre-coded models for routers, wireless nodes, and communication channels. To construct the network structure, engineers select the specific INET modules and lock them into place, building a sprawling, interconnected map of the system. Once the structure is set, the engineer configures the behavior of the individual nodes. They assign routing protocols and set communication parameters, dictating exactly how these modules will interact. Then, the simulation is executed. Users visually track the flow of data in real time, watching traffic move across the network under simulated stress. While this visualization runs, the software's debugging tools capture performance metrics, measuring throughput, latency, and identifying exactly where packets are being lost. This modular assembly and instant metric analysis empowers engineers to prove a design's viability, identifying bottlenecks before a single physical cable is manufactured. The financial and operational benefits of this workflow are immediate. Organizations can slash hardware research costs and provide their research teams with a secure environment for unrestricted experimentation. As telecommunications evolve, OMNeT++ is being used to design technologies that do not yet exist in the real world. Take autonomous vehicle networks. Researchers use this software to simulate exactly how thousands of self-driving cars communicate their speed and position instantaneously to prevent collisions. The framework is also mapping out vast edge computing networks and IoT sensor webs, architecting the data backbones required for future smart cities. Telecommunications researchers rely on these simulations to push the boundaries of connectivity, specifically testing the theoretical protocols of upcoming 6G networks. This leads to digital twins. On the left, a live physical tower. On the right, its virtual clone, running continuously in OMNeT++. When AI identifies virtual errors, the simulation calculates optimizations, instantly providing a validated blueprint to adjust the physical infrastructure. The infrastructure of future connectivity starts long before the fiber optics are laid. It is currently being prototyped, tested, and perfected inside the virtual discrete events of OMNeT++.